kind of problems we should do next week and so on. I don't think it makes sense now because there are too many of us and we're all mostly local. We'll do it probably next week. But I do want to encourage all the people to continue coming to this program, and I promise you it will be just as exciting. So.
Well, thanks for inviting me to this talk. I'm not really quite sure what what I should be driving at in these talks. So I hope to get plenty of feedback direct me about it. As I don't want to be telling you things that you already know or don't want to know. Well, let me just start off, but please interrupt. And I hope we can use the time in the best way. So we're considering Floer theory. Perhaps let's just discuss the historical, quasi-historical background. To this work of these ideas introduced by Andreas Floer. In the mid-1980s. What I mean by quasi-historical is that maybe it's not clear what I'm going to say was actually in Floer's mind or the mind of other people, but they were ideas that were around and being developed sort of in the pot of ideas that were being developed around that time. And they do, at least in hindsight, all fit together in a coherent way. And one important theme came from Arnold, because the Arnold conjecture in sympathetic geometry. Which again has a background in Hamiltonian dynamics, theorems of Poincaré on the existence of periodic orbits under certain conditions. And so this has to do with a symplectic manifold M, perhaps even just a torus, then in one version of the conjecture, considering dealing with symplectomorphisms. Satisfying, not going to an exact symplectomorphism. Then the conjecture was that the fixed points of this thing satisfy more constraints than you would get from the fixed points of a general smooth map. We take the number of fixed points. Fine, let's suppose this is a sort of super generic, so the fixed points are isolated. What we would know in general, just for a smooth map, is that this must at least be the Euler characteristic. These maps are all isotopic to the identity. But in fact, this conjecture is at least the sum of the Betti numbers. Okay. So the symplectic condition requires more fixed points than you would have for just a general smooth. Another piece of background is called the Castle Invariant. Of certain three manifolds, in particular homology three spheres. And you can think about this in terms of a special property that the fundamental groups of three manifolds have. You say, what is a three manifold? M3. What is special about pi 1 of M3 among all finitely presented groups? Consider. And there's a special property that comes from the existence of a Heegard decomposition. As well known, we can write a three manifold as the union of two standard pieces, standard handle bodies, glued together along their boundary, which is a surface, there's G. And then, if we do that, we have a presentation for the fundamental group of the three manifold as the fundamental group of sigma divided by the things that vanish on either side. In this handle body, the generators of the subgroup of sigma that is the torus. So, in Sigma's case, we have two generators for the subgroup of the torus. In the handle body, one of them vanishes. So this gives a presentation pi 1 of them with 2G generators, the standard 2G generators for the fundamental group of the surface, but also 2G relations. Coming from G either side. Whereas for a general finely presented group, there's no reason why you should expect to be able to find such a presentation with the same number of generators and relations. So this is something special about three manifold fundamental groups. And then Cassen's idea, perhaps following up this point of view, is that means that it should make sense to count the representations of the fundamental group of three manifold in some compact Lie group, or so to say, matrix representations. Count. Matrix representations of one of them. If we took any finely presented group, supposing we'd have some generators, and so we take corresponding matrices, say A1 to AR, and then we'd have various words of these things is equal to 0. But if we had, say, many more relations than generators, this will be a very overdetermined system of equations for our matrices. So perhaps we'd say we don't expect to find any of these things. Because this property of three manifold groups, in some sense, we expect to find isolated representations of the fundamental group in some sense. We'll come back to discussing that. Another point of view is in terms of four-manifold theory. About this time, it was known that if we look at closed four-manifolds, there are many things one can say about these using properties of the Yang-Mills instantons. For example, for a closed X4, so one kind of thing would be to say, if we have an intersection form, is say negative definite, so to say. Therefore, it's the standard form. So we can't the intersection form on H2 of X. So if we take the one example would be the form E8, it's a non-standard negative definite form. Which you probably all know I can write down. But so if you take some configuration of, say, spheres or surfaces intersecting according to the E8 form, and you try to build a form manifold like that, so you say you build then you can never build a closed form manifold with precisely this two-dimensional homology. But you certainly can build a form manifold with boundary. So you can certainly have a form manifold with a boundary, with some E8 intersection form. It's just that we can't make the boundary a three-sphere because then over the object category. So we could ask, what are the special? Can we say something more detailed about the relation between three manifolds and the four-dimensional things that they bound? Somewhere going beyond just saying the three manifold is not a sphere. Or equally similar. Let's just take that as an example. So this Floer theory, as originally developed, had two variants, one symplectic, which is the discussion relevant to the NULL conjecture. The point is that one could introduce some new homology groups which are associated to this symplectomorphism, and the invariance of these gave the constraint appearing in Arnold's conjecture. The other version is in gauge theory. Originally for the instanton, Yang-Mills instanton, equations, related to the Yang-Mills instanton equations, but then subsequently variants involving Seiberg-Witten equations, or further variants introduced by Orsvarth and Sabo, called Heegard Floer Homology. And probably yet other developments still that I settle about. But let's mainly talk about this this version of the theory. But many of the constructions translate from one. There's a comment of different versions, but we translate many of the ideas from one situation to the other one. And indeed, you can conceive of some abstract setting in which you could refine a Floer theory involving geometry and topology in a certain class of infinite-dimensional spaces. you could conceive of developing some abstract story which would all of these would fit into. So what we're discussing are the Floer homology groups associated to at least at a schematic level, to a three-manifold. Later we'll be more precise about what kind of manifolds we want to consider. But before trying to say anything remotely technical, let's just say that the different points of view, different ways we can motivate the constructions. Section 3, three different. Of course, related points of view. One point of view would be the sort of infinite dimensional homology. So one can see why something like this could be, just from the general nature of things. Supposing we're considering full manifold, let me say x1, divide the two pieces by a three manifold, then just treating the equations and things we write down entirely schematically, we want to look at to solve connections on X, satisfying the instanton equation. But we can think of these as the solutions on x0 and solutions on x1 for the same boundary value on y. So it doesn't matter for this schematic discussion, what the equation is. We're just saying if you want to solve an equation on this manifold built of these two pieces, the way of thinking about that is if we solve the equation on x0, we solve the equation on x1, we seek the solutions which will agree over y. Well, trivial thing to say. But from that point of view, then, if we look at the corresponding set of all possible data over y, so this will be magically connections over y, then we would have some subset of things which are boundary values of solutions on x0. Say, L0 is another subset. The boundary, say L1, the boundary values of solutions on x1, and studying our problem on the closed manifold X to correspond to studying the intersection points of these pieces. So at some level, this is a rather trivial statement. But it motivates saying, let's supposing that we had something like a homology group in which these spaces of boundary values carried fundamental classes, then we could think of counting these intersection points as a homological intersection. So we could try to have a homological discussion corresponding to this picture. So we see homology such that the I carry fundamental classes. So the counting solutions X corresponds to a homological section. Of course, this couldn't be anything like standard homology because these things would be infinite dimensional spaces. But just in terms of the schematic picture, that's a good motivation. Another point of view, perhaps the, well, let's do the other point of view at the end. Let's do a second point of view, which is clearly has something to do with the first one. Supposing we consider the same picture, a pair of four manifolds accepting a three manifold, but now consider we're going to consider a metric picture. We choose a family of metrics in which we have a very long net, stretching the net. In a metrics, family of metrics GT in the manner indicated and T very low. So I can show, and we will come back to this in detail, that in this situation, if we're studying solutions of this instanton equation over such a manifold, then when we make T very large, the connections will become essentially flat in this middle picture. So we'll return to this later. Rho by the flat connections over Y, which are the same as correspond to representations of I1 of Y. And the basic geometric argument in this situation is to say when we're studying these instantons, if we let T go to infinity, then we get two limiting problems given by adding on, taking the x's and adding on infinite cylindrical ends, tubular ends. So we should have a theory in which we can study instantons on such manifolds which are asymptotic to one of these flat connections rho at infinity. And the basic idea is that studying the instantons on something like this, when T is very large, they're essentially given by gluing together something on x naught would limit this flat connection rho, and something on x1 that would limit this the same flat connection. So of course this is similar to the preceding discussion, but now we're only trying to work over these space of flat connections rather than this picture of four. So the idea we get from this is that we should have moduli spaces M rho of xi correspond to instantons on xi with some fixed limit rho, and the decomposition should be a statement like that for large, very large T, the mx defined using this metric gt should be the union over rho of m rho x1 times m rho of x2. So from that point of view, you could say we have certain information, for each row, we have certain information that we'd like to record from these spaces m rho of xi, and the Floer homology will just be the receptacle of where we can record that information in an invariant way. It will naturally be the place we can store this information, or the part of it which is independent of continuous deformations, independent of the choices of metrics on these pieces. So the Floer homology groups are places to store information from these things. A third point of view, which is perhaps the most standard one, is we want to do a version of infinite dimensional Morse theory. So this more precisely expresses in terms of what's called a Witten complex, or snail Witten complex. So this is the construction that was mentioned in the lecture a week ago of Andrew Long. If we're in some standard five-dimensional situation with a compact manifold X, the function f, the Morse function, this is a five-dimensional compact manifold. Then we have a finite set of critical points. And each critical point has an index. For each critical point, let's say, critical points, each we have an index of P. Is it? A non-negative integer. This is just the number of negative eigenvalues in the Hessian. So then in this approach to Morse theory, we say that we form a chain complex. We first take the groups as generated by the critical points. So, X. But we use the index to put a grading on this group. Grading. Index. And then we want to define a differential so that the homology gives us the ordinary homology of X. We define D. Zero and homology D is the ordinary homology of X. So this is done by counting the gradient flow lines. So we choose a metric. X, and supposing this is suitably generic. For our purposes of what we want. So we could define we have an ODE. The x dt is equal to the gradient of that x. So that we have a gradient vector field on our manifold, and this is just the equation for integral curves of that vector field. So if we have a Morse function, we just have a finite set of critical points, and it's a very straightforward fact that if we take the limit as time goes to infinity of any such solution, that will be a critical point. And similarly for time goes to minus. So x plus or minus. Under this critical solution. Conversely, if we take given x plus or minus, x plus and minus, we can consider the space M x plus or minus given by solutions of this problem modulo the obvious reparameterization of changing t to t plus constant. Flow lines from x minus to x plus, modulo t goes to t plus constant. picture. This will be the canonical picture. And let's down this. Here we have if we take this is our x to be this torus embedded in R3, and the f to be the projection to the vertical axis, the height function. Then we have one minimum of index 0, one maximum of index 2. There are two negative directions at the maximum, and there are two critical points of index 1. So the fundamental fact is that if we look at x plus and x minus adjacent indices, the indices differ by 1, then if we place ourselves in a suitably generic situation, then there will just be a finite number of these flow lines going from one to the other. So will just be a discrete set of flow lines going from discrete. If we set off in a typical direction from this thing, we'll come whizzing all the way down to here. If we choose our direction exactly right, we might land up here. Or we could choose it exactly right, possibly land up there. And so on. So the basic point is that this set will be finite if the index of x minus, which we know is equal to the index of x plus 1. Which way around did we say? We said our differential is decreasing degree, so we want it to be the other way around. Minus. No, let's take it over. So the definition of D is that the matrix entry of our differential between a critical point of one index and a critical point of index one different is given by counting the number of these the number of these flow lines. D by number of points in x plus x minus. But we should emphasize that will only make sense if we're in a super generic situation. We could choose some very special metric in which we have a higher dimensional space, or any kind of space of these flow lines, not a discrete set. In fact, more precisely, we want to arrange that these things are defined transversely, or something, so it's all made precise. That's one set of things to explain. Another is that if we wanted to define homology with mod 2 coefficients, then we could just do this, and we would count this number modulo 2. If we want to define homology with integral coefficients, then we'll need to have some theory for attaching signs to these points, and do a signed count. But these are things we'll take up in our critical context. This is the basic idea. So So that's a recipe, just to say we write down this map D given by these matrix entries, but what we want it to, why should that give the ordinary homology, or why should it give anything that's of a topological nature? The basic, I can say that. So of course, why does it first of all give a why is d squared equal to 0? Thing. Andrew will discuss this in this lecture. If we consider if the index of x plus is the index of x minus minus 2, so we're going between two things of index difference 2. So we get a, and let's suppose that the dimension of this space of flow lines would be 1, and we have a one-dimensional manifold, but this is not a natural compactification to a manifold with boundary, where the boundary points correspond to factorizations of flowing. We can flow from x minus to x plus, but we can, as a limiting version of that, we can flow from x minus to some y, and then flow from y to x plus. It's just that it takes us infinite time to flow from x minus to y, infinite time to flow from y to x plus. So this is only an asymptotic statement that we can consider. Family of flow lines go like this, which approach this factorized object, but spend longer and longer in the region of y. And when you translate that into the statement about the matrix entries, that's precisely take account of signs, if you're dealing with signs, and so on, that precisely becomes the statement. The d squared is equal to 0. That statement, the number of boundary points of this one-dimensional manifold, the boundary is 0 in a suitable sense. I've written mod 2, the number of boundary points is even. In simplest case, that becomes the statement d squared is equal to 0. Let's write this down. So e.g., mod 2 coefficients, then the number of boundary points of m x minus x plus is 0, modulo 2. That is that when we count these factorizations, we get an even number that precisely says that this matrix entry is 0, modulo 2. Right, so this was another introductory. We've got to so let's just maybe I'll finish today by just saying how these points of view relate, and then in the next lecture we'll start again and do things more properly and define connections, instantrons, and so forth. Let's just finish this introductory part today. The relation between I need to explain this, but I need to make a bit of a start on the thing. How are we going to go about this? Okay, so let's not. We'll be better to explain that in a short while. So let's make a start on that. defining. So let's just talk about four-dimensional geometry. Say we have a compact four manifold, imagine a four manifold, and a bundle like this one structure group G, and G is S2s. So there are two let's talk about basic things we want to recall. One is the Chern vane theory. Which, to say, if we have a connection A on P, then we write down a suitable invariant expression. Let's write this trace squared. This defines a characteristic class. So in particular, four dimensions, we can just integrate this into X, and this is a topological invariant. In fact, if I remember right, we should put a minus 1 over 8 pi squared to fit in with standard normalizations, and then this would just be the second Chern class of our bundle. Regarded as an integer when evaluated on this oriented format. So the other basic notion that we want to record is index theory. If we have a suitable elliptic differential operator coupled to our connection, we can take its index, which is an integer, a number. In particular, the relevant, what is the relevant operator for our discussion is if we're going to take the one forms on X with values in the bundle of Lie algebras associated to P, add P, bundle of Lie algebras associated to the adjoint representation of P, then we can take a coupled exterior derivative of this, mapping to the two forms, but then we can project to the self-dual two forms. So let's just say omega plus P. Let's call this D plus. So this is defined using the connection, because we have these three forms to take values in this bundle. And then also we have the naught forms. And the similarly, it's the covariant derivative, I think. So why are these things important? This is infinitesimal deformations of the connection. We have a connection A, and we have one form, so we could consider A plus A. But that we don't need infinitesimal, we can make these just deformations of the connection. That's what it's lying here. Then this operator represents the linearization of the instanton equation, the anti-self-dual Yang-Mills equation. The instanton equation f plus of A. 0, where this is the, this is just the self-dual part of the curvature of A. The equation, so if we look at the curvature of A plus A, that would be something like the curvature of A like this. So the linear part of the self-dual part of the curvature, as we vary in small deformation A, is given by this operator D plus A. The linearized equation, linearizing about small deformations about one solution A, given by D plus 0. So that's the role of this equation, this operator. Similarly, this operator, backing from the sections of this bundle of the algebra to the one forms, this is just represents the infinitesimal gauge transformations. So this complex of operators is important because it represents the linearization of the moduli problems, the solutions of the instanton equation modulo the gauge transformation are modeled on the kernel of this D plus modulo the image of dA, which is the same thing as taking the kernel of the intersection of the kernel of D plus with the kernel of the adjoint operator. So the upshot is that we get the linearized equation modulo gauge given by the kernel of D plus A direct sum star A. The one forms split out the alchemy to self-dual two forms plus the naught forms. The essential thing is this is an elliptic operator and it has an index which is given by a topological formula. The index of I will write down the exact formula in the next lecture, but what we want to recall is that the foundations of the the theory in 4 dimensions we want to discuss is that we have two different connections between the differential geometry and topology, one coming through the Chern-Bay theory, involving this integral of the trace of the curvature squared, and the other coming through the index theory, applied in particular to this operator arising from the linearized principal approach. Alright, this is a good place to stop. We'll see explain in the next lecture how developing the Floer theory of a 3-manifold involves understanding the 3-dimensional analogues of these ideas. For example, the analogue of the Chern-Bay theory will be the Chern-Simons functional, of course, on connections over a 3-manifold. Maybe we'll stop there. Start with the first one.